Today I'll be solving the final problem from the 2018 HSC Maths Extension 2 exam. And we've got a complex numbers question with a cubic polynomial. So we have alpha, beta, and gamma are the roots of p of x equals x cubed plus px plus q, where p and q are real and q is not zero. First question is to prove beta minus gamma squared is equal to alpha squared plus 4q over alpha. Okay, let's have a look at the first part. So the polynomial is, so we got x cubed plus px plus q equals 0. And the roots are alpha, beta, and gamma. Okay. In fact, we can just write the coefficient of 0 in front of the x squared to make it a bit more clear. Now, using the formula for the sum of the roots, the sum of the pairs, sum of the products of the pairs of the roots, and the product of the roots, we have the sum of the roots is equal to the negative 0 divided by the leading coefficient of 1, which is equal to just 0. And the sum of the products of the pairs of the roots is equal to p divided by 1. So leading coefficient again, so p divided by 1 is equal to p. Product of the roots is equal to negative of the constant term, which is q, and divided by 1, so we just have negative q. Okay, so alpha plus beta plus gamma equals 0 gives us that what's it called, minus alpha is equal to beta plus gamma. And now we want to find beta minus gamma squared. Beta minus gamma squared is the same as beta squared minus 2 beta gamma plus gamma squared from expansion. But now we want to write this in terms of beta plus gamma and beta times gamma. So we can write it as beta squared plus 2 beta gamma plus gamma squared and minus 4 beta gamma. So now we've converted the negative 2 beta gamma into a plus 2 and minus 4. Now this factorizes into beta plus gamma squared minus 4 beta gamma. And now using this thing, we have minus alpha squared minus 4 beta gamma. And this is equal to alpha squared minus 4 beta gamma. And using alpha beta gamma equals negative q, we have alpha is equal to, beta gamma is equal to negative q divided by alpha. So that means we have alpha squared minus 4 times negative q over alpha, which is equal to alpha squared plus 4q over alpha. And this successfully proves the first part of beta minus gamma squared is equal to alpha squared plus 4q over alpha. So the first part is complete. And the second part is to show you need to prove this alpha minus beta all squared times beta minus gamma all squared times gamma minus alpha all squared is equal to negative of 27q squared plus 4p cubed. So one method I suggest is to consider the constant term of this cubic. However, the method I'll show you is slightly different. So you're allowed to use alternative methods. So it says hence or otherwise. So I'll show you an alternative way of solving the second part. Okay, so we have you want to find alpha minus beta squared times beta minus gamma squared times gamma minus alpha squared. And remember from earlier, remember from earlier, beta minus gamma squared was equal to alpha squared plus 4q over alpha. You can actually use similar reasoning since there's symmetry between alpha, beta, and gamma. You can use similar reasoning to get gamma minus alpha squared is equal to gamma minus alpha squared is equal to beta squared plus 4q over beta. And you also have alpha minus beta squared is equal to gamma squared plus 4q over gamma. So now this product will become, by replacing all the terms, we have gamma squared plus 4q over gamma times alpha squared plus 4q over alpha times beta squared plus 4q over beta. And this expands. Now we can take an entire denominator of alpha, beta, gamma, and we get gamma cubed plus 4q, alpha cubed plus 4q, and beta cubed plus 4q. Okay, so if I just rewrite the equation, so we've got the original polynomial was x cubed plus px plus q equals 0. And since alpha, beta, and gamma are the roots, we have alpha cubed is plus beta, alpha cubed plus p alpha plus q equals 0 by substituting alpha x equals alpha into the equation, which means we have alpha cubed is equal to minus p alpha minus q. So this means we can actually replace alpha cubed with minus p alpha minus q. And similarly, beta cubed is minus p beta minus q, and gamma cubed is minus p gamma minus q. So we can actually substitute all of those expressions in, and we have minus p gamma minus q plus 4q times minus p alpha minus q plus 4q times minus p beta minus q plus 4q is divided by, remember from earlier, alpha, beta, gamma was equal to minus q. That was minus q. Now we have minus p gamma plus 3q, minus p alpha plus 3q, and minus p beta plus 3q divided by minus q. Now we can expand this entire thing on the numerator. So to expand it, we can do the alpha, beta, gamma term, which is going to be minus p cubed times alpha, beta, gamma. So that's by doing these three things multiplied together. Now you can do the alpha beta plus beta gamma plus gamma alpha stuff. So an example is this term over here, and there's three of those terms. You'll end up having plus 3qp squared of alpha beta plus beta gamma plus gamma alpha. And now we can look at the alpha plus beta plus gamma term, which is we have 3q and minus p alpha and 3q here, which means it will be minus 9pq squared alpha beta gamma. What's it? Alpha plus beta plus gamma. And the final term is going to be the plus 27q q cubed. And now you divide by negative q. And since we know we have all the expressions for these terms, so we can just substitute it in. We have minus p cubed, and alpha beta gamma is minus q. And 3qp squared alpha beta plus beta gamma plus gamma alpha is p. And minus 9pq squared, so this thing was equal to 0, and plus 27q cubed divided by negative q. And when you divide by negative q, you'll get minus p cubed minus 3p cubed plus 27q cubed, which is equal to the, oh wait, this should be 3q minus 27q squared, and this is equal to minus of 4p cubed plus 27q squared. Okay, and that completes the second part. So second part, we've proven this left-hand side over here is equal to the right-hand side. Okay, so the part 2 is complete. The final part is to prove if 27q squared plus 4p cubed is less than 0, then the equation p of x equals 0 has 3 distinct real roots. Okay, let's have a look. So we have x cubed plus px plus q equals 0, where p and q are real numbers. And what we always have is a cubic polynomial with real coefficients always has at least one real root. So at least one of the numbers alpha, beta, gamma are real numbers. And we can say without loss of generality, so since there's symmetry between A, B, and C, alpha, beta, gamma, without loss of generality, we can say let assume alpha is a real number. Okay, but now we'll do a proof by contradiction where we say assume we don't have 3 distinct real roots. Okay, first we'll assume we won't worry about a distinct condition for now. We'll just assume we don't have 3 real roots at all. And now by the complex conjugate root theorem, the roots must the non-real roots must come in conjugate pairs. So it means beta and gamma are conjugates, assuming we don't have 3 real roots. So beta and gamma are both non-real complex numbers. So we can let beta equal x plus iy and gamma equals x minus iy. And so x and y are real numbers and y is not equal to 0. So now we can substitute all this into the previous part of the previous question, which was this one. So we have 27q squared plus 4p cubed. Now alpha minus beta. So what's alpha minus beta equal to? Alpha minus beta, we have this new substitution for beta. So we have alpha minus x minus iy. Beta minus gamma is equal to 2iy. And gamma minus alpha is equal to x minus iy minus alpha. So this is the same. And now, so 2iy squared is the same as 4 times I squared, which is -1 times y squared. So you have -4y squared times a minus x minus iy squared. And I just take the negative of the inside part, so it won't change the number because we are squaring it. So instead write a minus x plus iy squared. And this is the same as -4y squared. And now I'll multiply the two things and square them at the end. So I'll take both of them on the inside and then square them. And now I have -4y squared. And this, in fact, is a difference of 2 squares because we have alpha minus x times alpha minus x, and then this minus iy and plus iy. This is equal to -4y squared. So we have alpha minus x squared, and so I squared is -1, so we have this thing. Okay. And now remember, y is not equal to 0. And since y is not equal to 0, it means that y squared is greater than 0. So that means you have a y squared here and a y squared here. So that's greater than 0. And alpha minus x is at least 0, which means, alpha minus x all squared is at least 0. And we have a minus 4, which is negative at the front, which means this entire expression is less than 0. And remember, the right-hand side of the expression was negative 27q squared and plus 4p cubed. That means negative 27p squared plus 4 cubed has to be less than 0, which means 27p squared plus 4 cubed is greater than 0. However, the conditions of the question say, we are saying if 27q squared plus 4p cubed is less than 0, so we are only considering when this occurs, so it has to be less than 0. However, when we assumed we don't have 3 real roots, we got that it's actually a quantity 27p squared plus 4q cubed is greater than 0. This is in fact a contradiction. So this is a contradiction, and it actually means all the roots are real. So all 3 roots actually have to be real. The final step is to show the roots are all distinct. And the reason for this is, if you go back here to this equation, what we can see is the 27q squared plus 4p cubed is less than 0. And this means that negative of 27q squared plus 4p cubed is greater than 0. This means the right-hand side is not equal to 0. And that means in the left-hand side, none of these 3 things can be 0, because then their product will be 0. That means alpha minus beta is not 0, beta minus gamma is not 0, and gamma minus alpha is not 0, which means no 2 roots are the same. So all pairs of roots are different. And this means all 3 roots are distinct. So we've finally proven the 3 roots of this quadratic are all different and are real numbers. That concludes the proof for this HSC final question. So hope you enjoyed the video. Thanks for watching, and I'll see you next time.